sun is the driver of life on Earth. This intense ball of energy helps sprout new plants, drive our sleep cycles, create weather patterns, and even give our body vitamins necessary for us to function. But how can we harness this powerful energy source to help end the current energy crisis that is affecting our world and worrying so many of our planet's leaders and scientists? Currently, we try to do this through solar panels, but those can only gather so much of the sun's energy, and to produce large amounts of energy, we would need tons of them, covering large amounts of land that could be used for other purposes. But what if instead we use the internal processes of the sun to create our own power? What if we try to make our own sun right here on Earth? Through fusion, we're accomplishing something very similar. One place where they're creating fusion is here at the Princeton Plasma Physics Laboratory. This is Arturo Dominguez, part of the Science Education Department here at PPPL.
The main challenge is that what we're trying to do is, if you think about it, very extreme. We're trying to make on Earth a sun that's effectively 10 times hotter than our sun.
Fusion is the process in which atoms, like hydrogen, come together and fuse, releasing large amounts of energy. To do this on Earth, however, scientists have to heat up the atoms to super hot temperatures, even hotter than the sun. When hydrogen gas is heated up that hot, the electrons separate, and it creates this charged gas called plasma. These temperatures, the particles in the plasma are moving at great speeds and colliding, a wild soup of charged particles. But for fusion to occur, we need to contain this crazy hot soup, keeping the particles close enough so they collide and fuse together, releasing the energy that we want to collect. But how can we contain and control something that is 6 to 10 times hotter than the sun? The answer? Magnets. Well, how can magnets help us control the super hot hydrogen plasma? Turns out magnets don't only affect metals, but also moving charged particles. And our plasma is full of those.
Similar to, for example, the northern lights, that you have the magnets, the magnetic fields going from the south to the North Pole. The plasma will get stuck on the magnetic field lines and move both to the North and the South Pole.
Look, as the plasma bends and compresses as a magnetic field is produced through the coils. This effect is critical for magnetically confined fusion, keeping the plasma controlled and contained and ready to create fusion.
What it actually looks like is if you've got a magnetic field going in a certain direction, like here, like in my arm, then the electrons and the ions will spiral around that magnetic field. So it's a way of confining plasma to stick on this one direction of movement. Now, if we get that one direction of movement and turn it into a torus, then we have a toroidal confinement of plasma.
Here at the PPPL, they use what is called a tokamak reactor, which comes from a Russian word describing the donut shape of this magnetic chamber. Using special coils in and around the donut, a magnetic field is produced through the inside of the tokamak. The plasma particles then spiral tightly around the magnetic fields, staying contained in a small space and off the walls of the reactor. Fusion doesn't produce CO2 greenhouse gas emissions. Plasma is produced from abundant resources. It's safe, and there's no long-lasting radioactive waste. So with fusion being such an attractive source of energy, why aren't we using it more to produce a large amount of the world's energy?
Well, I see fusion as being one of the integral sources of energy in the future. Now, it won't be in the next few years, but I think in about 30 to 40 years, we would have fusion energy in the grid, and it would be a good baseload energy that could supply anywhere in the world.
The problem right now is the amount of energy captured from the fusion is less than the amount used to heat up the plasma. But technology is improving, and more research is going into making a fusion reactor that produces a positive output of energy. When we accomplish this, fusion may take the forefront in our mission to find the energy source of tomorrow.
We need to get plasma really hot in order to make fusion happen and have more output than the energy that we put in. So the technological challenges are very great. And a lot of research has been done, and we believe that the current physics, the understanding of physics is good enough to actually get to this goal of break even and of ignition. But but we need more investment, and we need to be able to have the funding to make the machines that we need for the future.
The sun is our most generous source of energy. If only we could truly appreciate its power here on Earth. But with the help of magnets and fusion reactors, maybe one day soon, we will.